In this video, we're going to discuss three methods that we can use to calculate the concentration of an unknown sample using a standard or a set of standards. The first step we want to take is to prepare a set of standards that span the analytical measurement range or linear range of the assay. The product insert provided by the manufacturer will tell us that range. On the right, the Point Scientific glucose oxidase assay product insert is shown. We can fill out the table below based on the product insert and the equipment and materials we have in our lab. Our lab has a 500 milligram per deciliter glucose standard and micropipettes that can accurately deliver volumes as small as 10 microliters. When we look at in the limitations section of the insert, we see that the linear range for this assay is 0 to 500 milligrams per deciliter. We can put this range in our table so we know the concentration range our set of standards needs to span. When we make our standards, we need to ensure that we prepare enough volume for the procedure, including some extra for dead volume. When we look at the procedure, we can see that this procedure requires at least 10 microliters of sample per reaction tube. We can fill this minimum volume into our table, and now we are ready to calculate how to prepare a set of standards that span the assay's linear range. When we make a set of standards, we want to prepare at least 5 standards that span the linear range of the assay. In the table on the bottom left, I have selected a range of concentrations that span the assay's linear range. We can use the equation C1 times V1 equals C2 times V2 to determine how to prepare this set of standards. When we use this equation, we need to factor in the final volume of standard we need, as well as the minimum volume our micropipette can deliver. For example, to prepare the 250 milligram per deciliter standard, we want to ensure that we are preparing sufficient volume of standard for the procedure. I think that making 50 microliters will provide sufficient volume and stay within the limitations of our micropipette. We will set up the equation with the variables that we know, which include the stock standard concentration, the final volume we want, and the concentration we want. Then we can solve for the volume of stock standard that we need to add to make the 250 milligram per deciliter standard and insert that volume into our table. Next, we can calculate the volume of diluent we need to add to the 250 milligram per deciliter standard by subtracting the stock standard volume from the total volume. And we can insert that 25 microliter volume into our table as well. In the next example, to prepare the 50 milligram per deciliter standard, preparing 50 microliters of standard would result in us needing to pipette a volume smaller than 10 microliters, which we can't do with the micropipette we have available. Instead of solving for the volume of stock standard we need to add to make the standard, we are going to set the stock standard volume to 10 microliters, the minimum volume our micropipette can deliver, and solve for the standard's final volume. After solving for V2, we determined that we need to prepare 100 microliters of the 50 milligram per deciliter standard. We can put the 10 microliters of stock standard into our table, and lastly, we can calculate the volume of diluent we need to add to the 50 milligram per deciliter standard by subtracting the stock standard volume from the total volume, and we can insert that 90 microliter volume into our table as well. Now that we have completed our calculations on how to prepare our set of standards from the 500 milligram per deciliter stock standard, we can make the standards and assay them along with our unknown samples in the glucose oxidase assay. These unknown samples will include our patient samples as well as quality control samples. For brevity, I've only included the results from a single unknown patient specimen. You can see the absorbance results that were obtained for the set of standards and the patient sample in the table on the right. There are 3 methods we can use to calculate the concentration of an unknown sample from a standard or a set of standards. We will discuss each method in more detail on subsequent slides. Method 1 relies on plotting a standard curve and determining the concentration of the unknown from the line of best fit. Method 2 is based on Beer's law using a single standard. And method 3 is also based on Beer's law, but it utilizes a set of standards and their absorbance and concentration to generate a conversion factor for each standard. The conversion factors for each standard are averaged together and the mean conversion factor is used to determine the concentration of the unknown. We can plot a standard curve by hand by plotting the absorbance that we measured in our assay on the x-axis and the concentration of the standards on the y-axis. Once the standards are plotted, we can draw the line of best fit. The line of best fit should go through the origin. The line should be angled so the standards are on the line, or there is an equal number of points on both sides of the line that are an equal distance away from the line. After drawing the line of best fit, you should examine the line and data points to ensure that there is no loss of linearity at the higher concentrations. Next, we can plot the absorbance of the unknown samples on the line of best fit. The yellow circle on the chart denotes the location of the unknown. Then we can estimate the unknown's concentration by drawing a horizontal line from the unknown to the y-axis. Based on the graph, this patient has a glucose concentration around 158 milligrams per deciliter. We can also plot a standard curve using a computer software like Excel. The absorbance of the standards are plotted on the y-axis, and the concentration of the standards are plotted on the x-axis. We can use the program to plot the line of best fit going through the origin. The program can display the equation of the line of best fit. We can use that equation to calculate the concentration of our unknown samples by plugging the unknown's absorbance in as the x variable and solving the equation where y is the concentration of the unknown. Using the equation of the line, the unknown has a concentration of 154 milligrams per deciliter. The second method we can use to determine the concentration of an unknown sample is based on Beer's law, which describes the linear relationship between concentration and absorbance. Usually when we are using this method, we have only prepared and tested a single standard. It is very important to test quality control samples when using a single standard to determine the concentration of patient samples, because if the standard's absorbance is inappropriately high or low, the quality control samples will fail and their error will be caught before patient results are released. If a quality control sample is not used, an inaccurate absorbance value for the single standard will cause inaccurate patient test results to be reported. Assuming we only prepared a 250 milligram per deciliter standard, we would calculate the concentration of our unknown samples using the following equation. This equation is derived from Beer's law. The concentration of the unknown is calculated by taking the product of the unknown's absorbance and standard's concentration divided by the standard's absorbance. Using the data from the 250 milligram per deciliter standard, we can calculate that the patient's glucose concentration is 152 milligrams per deciliter. The accuracy of these results are tied to how accurately we prepared and tested the standard. If we tested multiple standards, we need to select a single standard to use to calculate the concentration of the unknown. We would select the standard that has an absorbance that is closest to the absorbance of the unknown, since that should yield the most accurate results, assuming the standards were all prepared and tested appropriately. Based on the data in the table, the 125 milligram per deciliter standard has an absorbance closest to the unknown. When we use the 125 milligram per deciliter standard in the equation, we get a concentration for the unknown of 163 milligrams per deciliter. We can see that there is a significant difference in the unknown's concentration based on which standard we use to calculate the unknown. Please note how using the standard with the absorbance that was closest to the unknown's absorbance resulted in a concentration that is more consistent with the concentration we calculated from the equation of the standard curve. The last method we can use to determine the concentration of an unknown sample is also based on Beer's law, but utilizes the data from all the standards that we tested. When we use the equation below to calculate the concentration of our unknowns, we are actually multiplying the unknown's absorbance by a constant conversion factor for the standard. The conversion factor can be calculated as the standard's concentration divided by its absorbance. We can then multiply each unknown's absorbance by this conversion factor. When we have a set of standards, each standard will have a slightly different conversion factor. In a perfect data set, the conversion factor would be identical for each standard, but we rarely live in a perfect world. We can calculate the conversion factor for each standard. Ideally, the conversion factor should be very similar to each other in a set of standards. Any conversion factor that is discrepant from the rest indicates that an error occurred in preparing or testing that standard. We can take the average of the conversion factors and use this mean conversion factor to calculate the concentration of our unknown samples. When we use the mean conversion factor to calculate the concentration of our unknown samples, it is as if we calculated the concentration of the unknown sample with each standard and then averaged those concentrations together. This mean conversion factor also estimates the slope of the line of best fit if we were to graph the standard curve with concentration on the y-axis and absorbance on the x-axis, since slope is the change in y values over the change in x values. Remember in method 1 that the slope of the line of best fit was 400 for this data set, and the mean conversion factor for this data set is 401, proving that the mean conversion factor is a good estimate of the slope of the line of best fit. To calculate the concentration of our unknown sample, we multiply the absorbance of the unknown with the mean conversion factor. When we use our data, we get a patient glucose concentration of 154 milligrams per deciliter. This method is faster than calculating the concentration of each unknown with every standard and then averaging the results, and is a great method to use if you don't have access to a graphing software to determine the equation of the line of best fit. One caveat with this method is that the mean conversion factor is accurate if the conversion factors for the standards are similar to each other. If there is an outlier, it will skew the mean conversion factor and cause inaccurate results. So you always want to examine your mean conversion factors and make sure they're similar to each other before using this method. If there's one that's clearly an outlier, you would drop that one and not use it to calculate the mean conversion factor. This slide demonstrates how using the mean conversion factor is identical to calculating the concentration of the unknown with each standard and averaging the results. On the left is the conversion factors for our set of standards and the concentration of the unknown we calculated on the previous slide using the mean conversion factor. The table on the right shows the concentration of the unknown when each standard is used to calculate its concentration. When we average those individual concentrations together from the table on the right, we get the exact same concentration for the unknown as when we used the mean conversion factor. The table above shows the unknown's concentration that was determined by each method we discussed. Plotting a standard curve in Excel or on an equivalent graphing software and using the equation of the line of best fit to calculate the concentration of the unknown is considered the gold standard or most accurate method. Plotting a standard curve by hand is error-prone and time-consuming, and you are relying on your ability to accurately estimate the concentration from the graph, which makes this our least preferred method. The single-point standard method is the easiest method to use, but the concentration of the unknown depends on which standard you used in your calculation, and any issues with the standard will affect the accuracy of the patient results. The mean conversion factor method is a good blend of ease of use and accuracy when a graphing software is not available, so long as there are no outliers that skew the mean conversion factor.